Okay. I think there's no bell today for some reason, so we start without it. Today's topic will be the so-called Gauss-Bonnet theorem. I already had it on the blackboard in roughly sketches, and it says the following, that if you have the Gaussian curvature, you integrate it over the whole surface, and you normalize it by 2 pi, then what you get on the right-hand side is something in terms of the number of holes in S. So it's like shifted by 1 and with this leading factor of 2. So like once you take the total Gaussian curvature of the surface, you get something that measures the holes that are in the surface. And today's lecture will be about like how to show that and like give you some intuition where this is coming from. But before we do that, I would like to tell you why that theorem is like so important that I spent the last lecture on it. And or maybe we start with an example. The simplest example is the sphere of radius r. In that case, we have the Gaussian curvature to be just 1 over r squared, what we had quite often. So what we get on the left-hand side is 1 over 2 pi, and then integrated over 1 over r squared dA, and then we integrate over the sphere of radius r. This, so we can bring out the 1 over r squared to the front, and then we get like here, that's the whole area of the sphere, and that's of course 4 pi r squared. And so what you end up with is that the 2 pi cancels, and in total you end up with 2. And that's consistent with at least my image of the sphere, that it doesn't have any holes. So that's an example. And maybe this calculation kind of convinces you why we need like this factor of 2 pi there in front to normalize it, because you get like something like in the first approximation where you have constant scalar curvature, constant Gaussian curvature, you bring that out, and then you get something that is like the area. Okay. I'm too fast, or like the clock is too late? Okay. Anyway, okay. So that's the theorem, and the example is nice. It works out. A different example would be the torus. The torus has a number of holes which is 1. So this on the right-hand side we get 0. So for the torus, the theorem says that the Gaussian curvature integrated over the torus has to be 0. So that's already a bit more, like non-trivial. At least it's not very obvious. Of course, we had it already that if you take the cross section of the torus, then we had here, that these sides has like different Gaussian curvatures. But sorry, the other, like one side. So if you take the cross section of the torus, then one of the sides has like Gaussian curvature +1, and the other side has Gaussian curvature which is negative. It's then maybe it's still like you have to check that, and it's actually non-trivial calculation to check that if you integrate over that, then both contributions cancel out immediately and exactly. So that's at least like from that plus and minus, you can maybe get like the first idea that it might be 0, indeed. So that's like some examples, like the easiest ones at least to check that theorem. So let's look at the Gauss-Bonnet and think a little bit of why that theorem is like so crucial. And the first one is that here we have local information. In order to measure the Gaussian curvature, I just need to look at like my surface in a small neighborhood, analyze it, and then like I get the curvature of that. Say, for example, I can measure it with like some geodesics. So that's like local information that I can measure locally. And then if you integrate it, you get something like that happens to be very global, like the number of holes. For that, you need to know the whole surface. So that's the first kind of like perhaps a little bit surprising thing is that this right-hand side, the left-hand side is local information, which is then integrated. While on the other hand, the right-hand side, this one is completely global. You will never be able to say how many holes are in a surface if you only know like local information. And so that's, in some way, it's like easy to measure. And that's usually a bit harder. So depends, of course, like what kind of data you have. Sometimes it's obvious that it's a torus. But usually, yeah, that's harder to measure, like the global information. So you can say that that's why this theorem is nice, is because we measure the Gaussian curvature, that's local, then we integrate it, we sum all of the contributions up, and then we get something global, which is usually a bit harder to determine. So that's like one way to see that, from local to global information. And then there are a few other very interesting properties. The next one is that if you change it, like if you slightly deform your surface, then the Gaussian curvature changes. Changes under deformations. So in particular, it's geometric. So, for example, if you have the round sphere, and you can like deform it and make like a little bit more looking like a handlebar here, where we have and then it's obvious that the Gaussian curvature of this one and this one is like very different, right? So, for example, here you produced like more positive curvature, but like on the other hand, like you produced also more negative curvature here. And then, for some reason, the theorem says these both contributions, they cancel out immediately, because under such a deformation, I don't create any holes. So these, if you integrate over all of that, you just don't see these effects. So these effects of like that you create a little bit more positive curvature at some point counterweight that you exactly had to create negative curvature somewhere else. So the other one is that holes are not created. At least on like normal deformations. So if you, of course, if you rip your surface apart, then you can create holes in there. But like under small deformations or just like continuous deformations, you will never create a new hole. And that's what it's called. Why this one was geometric. This one is what is called a topological invariant. So it stays invariant, like the number of holes doesn't change if you deform it. So it's like an invariant under these deformations. And if you're a physicist, then you might want to call that like some kind of topological conservation law. Like it's like conservation of energy and stuff like that. It's also if you change time, then the energy doesn't change. Here we have something like a conservation law where we say we change the shape of the operator and then something doesn't change. And that says that the number of holes doesn't change. So that's kind of like some conservation law. Because like one way, maybe I'll write that in the middle, is one way is that this result gives you also some constraint on what kind of Gauss functions you can get. So what kind of function, like a general question, I give you a function and ask you, can you find a surface that has this function as the Gauss curvature? And then, you know, from that thing is like, you can say, like, first of all, I have to integrate the whole thing and get like the total Gauss curvature, and then you see, okay, depending on the number of holes, I can realize that function or I cannot realize that function on a certain given surface. So it puts also some what functions can be realized as the Gaussian curvature on a given surface. Okay, so that's a few things, but like actually there are a little bit more information. So I continue writing it in this two column, where on this side we have something about KdA, and here we have something about the right-hand side, which is essentially counting the number of holes. The first thing here is like if I would have given you just the left-hand side, this expression, and I would have asked you what is that, and you would have said like, yeah, like an arbitrary real number, right? Like there's k, like definitely is something continuous. I can change it like slightly, like that's a continuous function. There's like can take values 1.5 pi and whatever at some points. But like for some reason, if you integrate all of that, what you get up is an integer. That's quite surprising, right? Like you have like a very continuous function, and then just if you integrate it, you always get like an integer that is just like the numbers of holes. So that's perhaps a little bit surprising. And here, on the other hand, like here, it's like obviously an integer. At least it's very hard to say what is half a whole. So, so that's like clearly like a bit surprising that one of them has like an integer and the other one not. There's also a few more things that are very strange. The first one is that k, the Gaussian curvature, depends on the first fundamental form. Right? So in order to say what the Gaussian curvature is, I need to measure the scalar product of vectors, and then we had like these whole things that you can calculate it from the connection forms and so on. But like the first ingredient was always we need a first fundamental form. While on the right-hand side, the number of holes, I don't need to measure any inner product of vectors. I just look at it and say like there's one hole or two holes. So this right-hand side clearly does not depend on the fundamental form. So I think that's mostly all of these special properties that I can think of, like why the Gauss-Bonnet is like in some ways very counterintuitive, and because these are like so counterintuitive properties, it's actually a very important theorem because it's something that is relatively hard to come up if you want to think about like how to prove that, or like how to even come up with that statement. It's already pretty ingenious because there's so many things that don't up naturally. Usually you have like something, you get an intuition by saying, okay, like this one relates to that one, so maybe I can build out of this, I can build like some data, and then I can compare these data if they depend on the same things. That's a not logical statement that like things that depend on the same thing might be related. But here you get things like something that depends on the first fundamental form, something that does not. Like why would you expect these two things to be the same? So in that way, it's very important. And the theorem in itself, I think, goes back to Gauss and Bonnet. I think that goes back to pretty early, actually. I don't know if Gauss was first or Bonnet was first, but at least like the dates that I wrote down at some point for like that they are connected there. But the theorem in itself is also very important because it gave rise to many, many other theorems that are of that form. So we have the following property that we have quite a lot of far-reaching generalizations. Or extensions of, and all of them are like kind of theorems of this form, that we have an integral over some local data, which is geometric. So in our case it was the Gauss curvature, but it could be something else. And it's usually defined via some auxiliary data. In our case, that's the first fundamental form. So you have these kind of information, and then you integrate over that. And these theorems then also usually tell you something, answer which is a topological invariant. That is like discrete or has some integrality. So for us, it was really that it's an integer if you normalize the left-hand side correctly. But like sometimes it's not as easy as really producing an integer, but like you get something more difficult, but still something that is kind of an integer or like discrete. And it does not depend on the auxiliary data that you use to define the left-hand side. So that's there are many theorems actually of that form by now. I want to mention two of them, which is the first is the Chern Gauss-Bonnet theorem. yeah, so Mr. Chen was a Chinese mathematician. It's around 1945, so it's still quite old. And it's essentially generalizing this Gauss-Bonnet theorem to higher dimensional objects. So if you don't think about like two-dimensional surfaces, but you ask yourself, okay, do we have something else like curvature for three-dimensional objects and then integrate it over that? Do we get also an integer? So that's what this theorem is doing. So that's the first generalization. I would say that's like very natural thing to ask yourself then, once you actually talk about what is the curvature of higher dimension objects. But that's quite intuitive. Then a far-reaching theorem or generalization is the Atiyah-Singer index theorem. Which was another 20 years later. And that's like a very, very far-reaching generalization. In that case, yeah, you have something on the left-hand side which is like actually given as some kind of operator in some Hilbert spaces, and it's a pretty complicated object actually. And then on the right-hand side, you get something that is called an A-hat genus. So that's some topological invariant that you can ascribe to your object. And then Atiyah and Singer showed that these two things are actually the same. So I just wanted to tell you that like these kind of theorems are by now very standard in geometry, and like if you want to continue studying geometry, then you will probably encounter one of them at some point. Okay, so that's, I think, for philosophical general remarks about the Gauss-Bonnet theorem. Now I would like to give you the proof, not because we want to prove everything in a lecture, but because I think like it's kind of important for you to see where like these kind of counterintuitive things get put together. Like how do you actually develop an intuition for something that is so counterintuitive? Is by like sadly, the only thing that I can do is tell you how you actually prove that, and then you like think about each of these steps, and then you get some intuition why they actually fit together. So that's the idea for today, or the plan. Okay, so the idea first is that we look exclusively on the left-hand side. So we just have a look at this kind of side, or like this kind of data, and try to better understand that in certain ways. So the first idea would be to say what happens on a small patch. So because we want to integrate over the surface, so one idea is we put like the surface, we make it small, like make it a union of small balls, say, or small rectangulars, and then we integrate like locally, and locally we can use our expressions that we had with the connection forms and so on. So that's the idea to get the left-hand side. So the starting point is we need to choose E1, E2, and E3 be a frame. Adapted to S, and we say it's positively oriented, which we had last time. So that's like it plays nicely with the orientation that comes from the area form, the area element. And then what we had last time, well, at some point, we know that we can write this kind of expression First of all, because it's positively oriented, we can write dA in terms of these our by now favorite elements, these dual frame. So frame. And then the area is given by just a wedge product. And here we can now use the Gauss equation to write this one as d of omega to 1 as in terms of the connection forms. So suppose that we have some say ball, and we go counterclockwise around it. That's the boundary. So like we go counterclockwise, and now we would like to integrate at least over that small ball. So we assume that the boundary is nice and smooth. What we can do now is we can integrate the left-hand side over this area over key dA, and then we can write it as by this calculation as the integral over b of the connection form. And now we use our Stokes theorem we had at some point, and we can write it as the integral of the boundary curve over this one form that is given by the connection form. So what is that integral is now the question. So first of all, one remark, so this calculation is valid for everything where we assume that we have a frame that is like covering the whole surface. Usually that's not really true. You have, like, for example, in the sphere, you don't have a frame that is covering the whole sphere, but you have like one maybe on the upper and one on the lower hemisphere. So in that case, this one is this calculation is valid for all B's which admit like a whole frame. So this calculation is valid for all B's that are covered by a global frame. So okay, but anyway, now we have the question like, what is this line integral? That's the next question. So first observation is that if c is a unit speed curve, which will be then of course the boundary in our case, and we assume that the frame is adapted to that curve, saying that you have c dot equals to E1. So if the frame points in the first direction is given by the curve c, then we have found at some point that if you now evaluate the connection form on that tangent vector of the curve, perhaps it's better to write this as a minus sign of 1, 2, evaluated out of the curve C of t. What you get is that it's minus the Gaussian curvature of the curve, geodesic curvature, sorry. So another simplifying condition, you have that this expression over here gives you the geodesic curvature. So if that simplifying condition is true, then what we get up here essentially is the whole geodesic curvature of the boundary of B. So what happens if you don't have that assumption? In general, what we have is that C dot is actually not just in E1, but it's like rotated by some angle. Cosine phi of t E1 C of t plus sine phi of t E2 C of t. Because it's a unit speed curve, that's always possible. And we had at some point, namely in the theorem on the proof of the parallel transport, we had expressions like that, and then calculated what was the covariant derivative of a vector field of that form. And what we ended up with was this general expression that the geodesic curvature is given as the phi of t, which is like the angle, like the variation of that angle, plus the connection form. So in this, the first case, we get like that the phi of t would be just like the constant, and then we have like the formula back that is up here. But in general, you get like some correction term that is coming from the angle, and that's the proof of the parallel transport. There we essentially calculated at least that the covariant derivative of a vector like this is given in terms of these data. So that's nice. So what we now want to do is we actually want to integrate over this expression. So we want to integrate it because this previous calculation said we want to have the integral over the curve, boundary curve over this omega 1, 2. So that's what we have. So we would like to get now an answer of what we would like to have in terms of these two data. So suppose that C is a curve from A to B into the surface. So the interval is just from A to B for simplification. So what we get up then is that the integral of the left-hand side of the geodesic curvature. So that's the geodesic curvature. And then we end up here with just the fundamental lemma. It's like the end phi of A, phi of B minus phi of A. and then minus the integral of this one form over the curve C. And we already discussed that, at least in this context of the parallel transport, this angle gives you the rotation angle of the vector. So in this case here, it's some form of a winding number. So you count how many times the tangent is like turning around once you reach, like you go around on the curve. So you're back to the same point, but the tangent might have like turned quite a few times during that time. And that's measured by this winding number there. So that's the result now, is that the total Gaussian, total geodesic curvature of the curve is given in terms of like this winding number and the connection one form. So that's this first important result. So we can, maybe it's also nice to do an example here. We can just say we take in the plane, we walk around a circle of radius r. Radius r. So that's a loop, and we walk around it counterclockwise. So in this case, the Gaussian curvature, why do I always say Gaussian curvature? It's the geodesic curvature of the curve is 1 over r, as we had like discussed quite a few times by now. So if you now calculate the left-hand side, what you end up with is, say, from 0 to 2 pi of 1 over r. And then here we have the assumption that it's ddt means the unit speed parameterization. So I can't just write theta there, but I have to parameterize this by unit speed, and that gives us an additional factor of air there. So this comes from the unit speed parameterization. So if you calculate that, that's the left-hand side, and that's, of course, just 2 pi. Of course, yeah. And that's consistent with the fact that on the plane, we just get this term being 0 because there's no, the connection form is trivial in that case. Because there's no curvature, intrinsic curvature of the plane. So that's an example where it works out. And if you now bring this discussion over here with what happens if you have like the integral over a curve of the geodesic curvature, and combine that with this calculation that if B has a global frame on it, then we can write it as this line integral. If you bring both of these things together, we get like the following local version of the Gauss-Bonnet theorem. So if you have S be a compact oriented surface, with area element given by dA, then what we discussed now was that for every subset B in S, which is small enough such that it admitting an adapted global adapted positively oriented frame So, for example, one way would be to say that it can be covered by one chart. That would be, for example, an admissible B. And then we say that the boundary curve dB is smooth. And we also need that it doesn't have any self-intersections, simple, and unit speed. So that's the boundary curve, say, from then, if you have all of these things, we have the following statement, namely that if you integrate the Gaussian curvature over that part of the surface, so it's important that it's here only over the small part of the surface, namely over B, then add the total Gaussian curvature, geodesic curvature, of the boundary curve. So what you end up with is 2 pi. So the picture is that you have a small b sitting inside. You walk around it counterclockwise, say, in your whole surface. And on B, you have a nice frame that is defined everywhere. But it might not be extend to all of S. So that's the ingredient, is that we really need like this frame, because otherwise this calculation doesn't work. If you don't have like a whole frame, then we can't write it in these terms, because the theta 1 and theta 2 are already only defined if you have a frame. So we always need like a frame adapted, and then we can do this calculation. But we don't know yet what happens if you have like a huge part, like for example of the sphere. It doesn't admit like a whole global frame, so we don't know actually what will happen. And the idea is that that we stitch together the surface from small parts, and then just calculate what comes out from each of these small parts, and then glue our surface together. And for that, it's the nicest is actually to cut your surface in triangles. So what we would like to apply is that to a triangle. So that would be B. But then we have a problem because the triangle in itself is not smooth. So here we said that we have a nice smooth curve. The boundary was smooth, and we needed that for the Stokes theorem to hold. So we need like a correction term, or there will be a correction term that comes from these non-smooth parts. And if you look at like a triangle, then you see that then what happens to, like say we walk around it like counterclockwise, what will happen is that you have the tangent which goes in this direction. So that will be the tangent if you walk around it. So that will be pointing up there. And then at that point where it's non-smooth, what will happen is that like the tangent turns around quite quickly. So you have like a jump of the tangent of the curve by some angle, and that angle is called like some angle in here. And that, of course, this like turning around is actually what will contribute here. If you start to do this calculation, that was still valid, but then like if you integrate it, you get another term, which is not just the winding number, but it like you will also sum up all these like turnings of the tangent like that comes from the piecewise smooth. So in this case, we get the following slight generalization. So theorem. And the same setting up both, but if dB is piecewise smooth and has interior angles, for I. So I don't want to give like the concrete definition, but it's just like you look at the tangent and you see like how much that turns around by some angle. So the picture, I think, is the easiest definition. You just look at the tangent and then you take like the angle that is like sitting inside the curve that measures you how much the tangent is turning at that point where it's not smooth. Then you get the following formula that we which in this case is so you get the angles would be so n angles. So like if you have like an n-gon, like a polygon with n edges, so here would be a 1, 2, 3, but you might have like something that looks like this. Then we have phi 1, phi 2, phi 3, and phi 4. That's the interior angles, and n is the number of jumps or like places where your curve is not smooth. So you get like some modification of this formula. You get the formula back if you set n equals to 0, because then this term vanishes and this term vanishes. But in general, you get like some contributions coming from the angles. Okay, and that theorem is quite nice because it allows us to just completely independent of like our objective with the Gauss-Bonnet theorem, it gives you some way to measure or like to say, to relate the Gaussian curvature of some, say, like a triangle. If you assume, for example, that the triangle is geodesic, so like all the boundary curves are geodesics, then the Gaussian geodesic curvature vanishes, so we don't get any contribution here. But then this theorem tells you that the total Gaussian curvature of like this triangle can be measured in terms of the angles in there. And so as a corollary, we have the following. Triangle. So whose edges are geodesic. Then we have the following formula, namely that the integral of the Gauss curvature over the triangle is the sum of all interior angles, and then minus pi. So that shows you, if you now bring over the pi over here, maybe we do that, we get that you can measure